In this video, we'll discuss structural aspects of benzene and what it means for a compound to be called or classified as aromatic. Benzene itself is the simplest aromatic hydrocarbon. Benzene and its derivatives were first called aromatic because of their pleasant smell, but as you'll see, the term aromatic has a much more specific chemical definition. Benzene, or a benzene ring, has 4 degrees of unsaturation. It has a ring and 1, 2, 3 double bonds, so that's 4 degrees of unsaturation. The 6-membered ring of benzene is planar, with all bond lengths being equal. The 6-membered ring has on every carbon a p orbital, so we have a cyclic array of conjugated p orbitals, which means that all of the electrons are delocalized, which accounts for the fact that all bond lengths are equal. We have 2 resonance structures for benzene, and the resonance hybrid would look something like this. Some textbooks will draw benzene with a circle in the middle of it, but when you're drawing benzene, stick to the structures that have double bonds drawn specifically, because that makes it easier to keep track of pi electrons when writing out reaction mechanisms. A few words about nomenclature of substituted benzenes. When studying for exams in Organic 2, I think it's best that you spend the least amount of time studying nomenclature. Spend more time on chemical and structural aspects of the functional groups that we talk about. Still, nonetheless, you should be able to identify and name simple mono and di-substituted benzenes. A benzene ring with one substituent, it has a simple way of naming it. Basically, you just name the substituent and add the word benzene to the end, as you see in these examples. Unfortunately, or fortunately, many monosubstituted benzenes have common names, and you really have to get used to those too. For example, here we have methylbenzene. If I was in the lab, I would never ask someone to hand me the bottle of methylbenzene. I would say, give me the toluene. These names are just so ingrained in chemistry that you really have to get used to it. So for example, toluene, phenol, aniline, those are pretty common. In the case of naming di-substituted benzenes, you have to consider the formation of isomers. It's possible to have 2 substituents on the ring, and one could be on C1 and one could be on C2. The C2 position is also called the ortho position. You could have a substituent on C1 and a second substituent on C3, and this is also referred to as the meta position. Again, you could have a substituent on C1 and one on C4, and these would set to be para to each other. So this is the ortho position, the meta position, and para position, and these terms will be used frequently throughout the semester. Here's some simple examples. You have a 1,2 or ortho disubstituted benzene, a 1,3 or meta disubstituted benzene, and a 1,4 or para disubstituted benzene. In terms of naming them, this could be called ortho dibromobenzene or 1,2 dibromobenzene. Ortho is abbreviated as O, and notice that it's written in italics. If you are writing it out by hand, you can just simply underline. So underline equals italics. This example would be called a meta dibromobenzene or 1,3 dibromobenzene. Meta is abbreviated as a small m, and you could have para-dibromobenzene or 1,4-dibromobenzene as names written out for this molecule, and the abbreviation for para is a small p. See your book for any further details regarding nomenclature of di and polysubstituted benzenes, but as I said, don't spend an inordinate amount of time studying nomenclature. We frequently see benzene as a substituent or part of a substituent attached to a larger portion of a molecule. Benzene itself, as a substituent, is called a phenyl group. Not phenol, but phenyl group. And it is frequently abbreviated as either C6H5 or capital P small h. How many degrees of unsaturation are present in a phenyl group? Well, it's a benzene ring. So regardless of whether it's a substituent or it's benzene, it's still 4 degrees of unsaturation. It has a ring and 3 double bonds. Sometimes benzene can be abbreviated as follows: C6H5 attached to H, or just phenyl attached to H. So remember, phenyl is this, and if there was an H attached, that would be benzene. For the molecule phenol, if we treat benzene as a substituent, we can write it out as C6H5OH, or much more simply and more commonly, just write it out as capital P small h attached to OH. So this would be the most common abbreviation for phenol. How would you abbreviate toluene using a phenyl group, using one of these abbreviations over here? Well, remember, toluene is methylbenzene, so you could abbreviate it as follows. You could either say C6H5 attached to methyl, or much more simply, capital P small h attached to methyl. So get used to these types of abbreviations. You're going to see them very frequently. Another very common substituent that you will see in molecules throughout the semester is a benzyl group. So remember, phenyl is just benzene itself as a substituent, but a benzyl group is a phenyl group attached to a CH2 group. So this whole group itself is called a benzyl group, and this would be called a benzylic carbon. Substituents derived from other substituted aromatic rings are collectively known as aryl groups. So anything that has a benzene ring and substituents attached to it could be classified as an aryl group, as a general class. Much like cyclohexane rings, benzene rings are ubiquitous in both naturally occurring molecules and also in synthetic molecules like the synthetic drugs that are shown on this page. Each one contains at least one benzene ring, and you're familiar with these. For example, Zoloft, Valium, Novocaine, Viagra, Claritin. All of these are commercial materials. This page shows you a number of naturally occurring molecules that contain a benzene ring, many of which you are already familiar with, that you encounter in every day. Benzaldehyde has the smell of almonds, the steroid hormone estrogen, adrenaline, the neurotransmitter, capsaicin, which is found in peppers. All of these are aromatic compounds. Benzene is much less reactive than typical alkenes or dienes, and its unusual stability is nicely illustrated here when we compare the heats of hydrogenation of cyclohexene, 1,3-cyclohexadiene, and benzene all the way down to totally saturated cyclohexane. When you hydrogenate cyclohexene, you end up with 28.6 kcals of energy being released. So that's one double bond, 28.6 kcals. When you move on to 1,3-cyclohexadiene, which has two double bonds, you might expect it to be 57.2. That is 2 times the amount of energy that was released when you reduced the single double bond of cyclohexene. But you have actually 55.4 kcals being released. So you have a small difference between the hypothetical and the actual heats of hydrogenations, only about 2 kcals. And if you go back to the chapter on conjugated systems, we explained the slight stabilization of this system because of the fact that these two pi systems are conjugated. They're next door to each other. So we have a little bit of delocalization of these pi, pi bonds, and so you have a little bit of net bonding, and bonding will lower the energy of the system. Moving on to benzene, you have 3 double bonds, so you might expect 3 times 28.6 or 85.8 kcals of energy being released. However, when you hydrogenate benzene in the lab, you only get about 50, 49.8. That's a big difference between hypothetical and observed heats of hydrogenation. And this can't be explained solely by the effects of resonance or conjugation. This extra stability of benzene is reflected in its reactivity toward electrophiles. Um, Benzene and related compounds share this unusual stability, and not only is benzene less reactive compared to alkenes and alkynes, but it actually reacts differently with electrophiles than alkenes and alkynes. For alkenes and alkynes, you normally had electrophiles doing addition to the double bonds, but in the case of benzene, instead of undergoing the typical addition reaction of unsaturated pi systems, it tends to undergo substitution reactions. So there's something about benzene that is making it markedly different than molecules that have carbon-carbon double bonds, other molecules that have carbon-carbon double bonds like alkenes and dienes. Benzene and related compounds that display this unusual stability and distinct difference in reactivity from other molecules that have pi systems like alkenes and dienes are said to be aromatic. Right? So this quality of aromaticity gives benzene and its derivatives unique physical and chemical properties. So again, we're not talking about the aroma of these compounds. The chemical definition of aromaticity is as follows. Any compound with a system of pi electrons that meets the following 4 criteria is considered to be aromatic, and it will have the extra stability like benzene does, and also the marked difference in reactivity. They undergo substitution reactions as opposed to addition reactions, as you'll see in the next chapter. So something is aromatic if it is cyclic, if it is planar, and it has to have all of these qualities, cyclic, planar, and there has to be conjugated pi systems. You have to have a contiguous array, cyclic array of sp2 or sp atoms that have p orbitals. So they all have to be conjugated. And lastly, the number of electrons in the conjugated cyclic array of p orbitals, the pi system, has to equal 4n plus 2 pi electrons, where n equals any integer. So basically what we're saying is 2, 6, 10, 14, etc. electrons, and this is just a device to come up with these numbers here. So any odd number of pi electron pairs will fit this description, and the Huckel rule, or the Huckel rule, will apply most specifically to monocyclic conjugated and planar systems. So these are the 4 criteria which are necessary for aromaticity. All aromatic compounds must be cyclic. It could either be one ring or many rings. No matter, each p orbital has to overlap with p orbitals on adjacent atoms within a ring. All aromatic compounds must be planar, that is, all adjacent p orbitals have to be aligned so that pi electron density can be delocalized, and the only way to do that is if you have parallel p orbitals. Take a look at 10-annuline. It looks like it meets all of the criteria. It is cyclic, it is, in this drawing, it's planar, it has a conjugated system, completely conjugated system, cyclic array of p orbitals, it has the Huckel number of electrons, 10 pi electrons. The problem here is that this bond angle is rather large. For sp2 atoms, the bond angle should be closer to 120. So 10-annuline, rather than existing in this planar conformation, will pucker and try to obtain this conformation. The problem here is the two hydrogens that are highlighted in red are bumping into each other, and that's preventing this molecule from adopting a planar conformation. It's actually puckered like this, so you have 1H here going up, 1H going down. So even though 10-annuline qualifies for 3 of the 4 criteria necessary for aromaticity, the fact that it doesn't meet all 4, the fact that it can't be planar, makes it non-aromatic. All aromatic compounds have to have completely conjugated pi systems. That is, p orbitals must overlap in a continuous closed loop of parallel orbitals. And as we've seen, the condition of planarity allows for effective orbital overlap so that you can achieve a completely conjugated system. For a molecule to be considered aromatic, not only does it have to be cyclic, planar, and completely conjugated, it has to also have a specific number of pi electrons in the conjugated system. 2, 6, 10, 14, 18, 22, etc., etc. That works out to 1, 3, 5, 7, 9, 11 multiple bonds. Rather than memorize all this, someone came up with this little device, 4n plus 2 pi electrons, where n equals an integer. So for example, if you say n equals 0, 4 times 0 is 0, plus 2 is 2. There's 2 electrons. If n equals 1, that's 4 times 1 plus 2, that's 6 pi electrons. If n equals 3, that's 4 times 3, 12, plus 2 is 14. If n equals 4, that's 4 times 4 is 16, plus 2 is 18, etc. So don't be confused by this. This is not n plus 1 rule in NMR. This is just a way to remember the correct number of pi electrons that must be in the system. And also, please remember that this refers to the number of pi electrons. This 4n plus 2 is the number of pi electrons, not the number of atoms in a ring. Okay, so if something is cyclic, planar, conjugated, and has 4n plus 2 pi electrons in that conjugated system, it is considered to be aromatic. And we said that aromatic compounds are especially stable. So here is benzene as a typical example of an aromatic compound. Something else that you have to keep in mind is that if a system is cyclic, planar, conjugated, but instead of having 4n plus 2 pi electrons, it has 4n pi electrons, those are considered to be anti-aromatic, and they are especially unstable molecules. So if a molecule has all 4 of these criteria, and it has the opportunity to, say, become non-planar, you bet it will. It doesn't want to become anti-aromatic. So this is something that molecules do not want to achieve. For this example here, cyclobutadiene, that's pretty much stuck. These 4 are 4 atoms with the double bonds in the ring. This must be planar. So this is a cyclic system. It is completely conjugated. It is planar, and it has 4 electrons. So n equals 1, that's 4. This is an anti-aromatic compound, and this is particularly reactive, very difficult to isolate. So remember, aromatic compounds are stable, and anti-aromatic compounds are unstable. And if a molecule can avoid becoming planar, it will do so in order to avoid being anti-aromatic. when considering which p orbitals to include in the electron count for Huckel's rule, you should consider only the largest closed p orbital loop. For example, you might look at this and say, well, this is a benzene ring and it is fused to a cyclobutene, and so therefore it's an aromatic system, and you've left these out. But these are actually part of the conjugated system, so this is not an aromatic compound. It actually turns out to be an anti-aromatic compound. Note that all of these p orbitals make up a continuous cyclic array of p orbitals, and so this double bond also has to be included in your count. Also note that the two orbitals that host pi electrons in questions have to be part of the closed loop, but the pi bond itself can be between any atoms within the loop. You might look at this and say, ooh, I don't know how to count this, but think about it. Each of these atoms that I'm circling around here with the laser pointer are sp2 hybridized, and each carbon in the ring has a p orbital on it. So this is just one resonance structure. If I change the resonance structure, you'll see that I'll end up with the double bonds all around the ring. So this molecule has 5 pi bonds, 10 pi electrons, 4n plus 2. It's cyclic, planar, conjugated. It is aromatic. It's quite common to see very large molecules that have fused benzene rings with lots of pi bonds in them. So when you see molecules with fused benzene rings, like the ones that you see on this page, consider them to be aromatic regardless of the number of pi electrons in the closed system. Right? So in general, molecules with greater than or equal to 2 fused benzene rings are aromatic regardless of Huckel's rule. Huckel's rule, when he did his calculation, specifically it was for monocyclic systems. So the Huckel's rule can sometimes even apply to bicyclic systems. So consequently, Huckel's rule only always holds true for monocyclic systems. When you take a look at these molecules, like for example, look at coronine. Is it cyclic? Yes. Is it planar? Yes. Is it fully conjugated? Yeah. Huckel's rule? No. 12 pi bonds, that's 24 pi electrons, that's 4n. However, it's still aromatic. So if you went into the lab and did some studies on it, you would see that it is aromatic. So this is something to keep in mind. When you have very large systems, you have more than 2 rings, and 3 of the 4 criteria are met. The 4th one, Huckel's rule, is not met. Well, again, Huckel's rule was specifically for monocyclic systems. So when you get to very large polycyclic systems, Huckel's rule is not necessary for aromaticity. In summary, molecules can be classified in one of 3 ways. They can either be considered aromatic, anti-aromatic, or not aromatic. So basically, we're saying they're neither anti-aromatic nor are they aromatic. For a molecule to be aromatic, it must meet the following 4 criteria, including the correct number of pi electrons in the conjugated system. For a molecule to be considered anti-aromatic, it must meet these 4 criteria, and the difference between an aromatic compound and an anti-aromatic compound are the number of electrons in the pi system. And then for a molecule to be not aromatic, it will lack one of these criteria. So you can put in molecules like methane or cyclohexane or 2,2-dimethyl propane, and you'll see that they're not aromatic because they're lacking, they're not cyclic, they're not planar, etc. So those are 3 classifications of organic compounds. Which of the following 4 compounds is aromatic? As usual, stop the video and see if you can provide answers before they're revealed. Starting at the top, of the 4 criteria, you need it to be cyclic, planar, conjugated, and 4n plus 2 pi electrons. Immediately, you can see that this cannot be aromatic because it is not cyclic. What about this one? It's cyclic, could be planar, it has the correct number of electrons. The problem here is it's not conjugated. This CH2 group is breaking up the conjugation. What about this? Cyclic. I don't see any reason why it wouldn't be. Planar. Okay. Conjugated. The correct number of electrons, 2, 4, 6, 8, 10, 12, 14. Okay. This one's aromatic. What about at the bottom? Cyclic, planar. Well, again, it's not conjugated. So the only aromatic compound would be this one. What about anti-aromaticity? See if you can pick out any anti-aromatic compounds in this list of 4. Well, we've already seen this one before. Cyclobutadiene. It's planar. It has to be if they're all sp2 hybridized carbons. It's cyclic, it's conjugated, and it has 4 N electrons, where N equals 1. What about this example? It's cyclic, it's planar, they're all sp2 hybridized carbons. It's a conjugated system, but the number of electrons it has, 2, 4, 6, this is actually an aromatic compound. This one obviously cannot be because it is not cyclic. Well, this one's cyclic, but look at the position of the double bonds. They're not near each other. They're not conjugated. Therefore, this is not anti-aromatic. One last problem. Are these compounds aromatic, anti-aromatic, or non-aromatic? If they're conjugated, draw all of their resonance structures. Again, stop the video, work the problem, and then the answers will be shown. The compound on the left is non-aromatic. It is planar, it is cyclic, but there is no conjugation going on here. This is a CH2 group. When we move over to this cation, we can draw resonance structures. Notice the positive charge is on this carbon, now it's on this carbon. Draw another resonance structure, now it's on this carbon. So this is a completely conjugated system. It's planar, it's cyclic, and it has 4n plus 2 electrons. N equals 0, there's 2 electrons in this system. This is actually an aromatic cation. What about the anion? As instructed, draw all resonance structures. I can push electrons around. I have a minus charge on this carbon. Now I have a minus charge on this carbon. Push electrons again, and I get a minus charge on this carbon. This is a completely conjugated system, as illustrated by these resonance structures. And it's a cyclic system. It's planar, but it has 4 electrons. That's a anti-aromatic number. So this is an anti-aromatic compound, this is aromatic, and this is non-aromatic.